Hello, welcome to Maths with EJD. In this video, I'll be talking about sensitivity analysis of a portfolio optimization problem. All right. So let's start out with the problem statement. The problem statement. Of course, from the previous video, you already know that you only talk about sensitivity analysis after getting your optimal solution using, say, simplex method. Of course, you can also use graphical method. My focus is on simplex method here. So here, the task, the task is to, the task is to determine, I want to determine the, okay, better still. Yeah, the task is to determine optimal proportions, the optimal proportions of a portfolio to invest of a portfolio to invest in to invest in three different assets to maximize the overall portfolio the overall portfolio return Z, right? While following certain constraints. Okay, so that's the overall thing. In addition, in addition, we seek to conduct sensitivity analysis. Okay, sensitivity analysis. Now, um, let's look. Imagine the objective function here. Objective function. So, we want to maximize the portfolio return, Z. That is Z equals 0.12 W1 plus 0.10 W2 plus 0.08 W3. So where where first of all W1, W2, and W3 actually uh, represent represent the proportions of the portfolio allocated to assets one, two, three, one, two, and three, respectively. One, two, and three, respectively. So the issue is you have some funds, you want to make investment. So you want to know what proportion should go to the first asset, that's the first kind of investment, what proportion should go to the second, and what proportion should go to the third. Basically, that's what that is about. Okay. Um, that's W3, right? So you want to know so these are proportions of each of the assets. Now we also have we have the expected the expected returns the expected returns for assets one, two, for assets one, two, and three are 12%. You can see this 0.12 is 12%. Then this is 10%, this is 8%, right? 12%, 12%, 10%, and 8% respectively. Okay, that's what we can see from the objective function. So that's about the objective function now. So let's talk about the constraints. Constraints. Okay. The allocation must satisfy the following conditions. So the first one is investment limit in assets one and two. So the combination of assets one and asset two should be less than or equal to 0.8. So the total proportion for assets one and two should be, so this is investment limit, investment limit in assets one and two. Okay. So then we also have another constraint. We have W1 plus W3 less than or equal to 0.8 again. Again, that's investment limit in assets one and three. Assets one and three. So the combination of assets one and three should not exceed 0.8. That should not exceed 80%. Then we also have W1 plus W2 plus W3. Of course, that's given. So it cannot exceed one. And that's the total. Everything it should not exceed one. That is actually the full portfolio investment, the full portfolio investment. Okay. If you add everything up, you shouldn't exceed one normally. That's 100%. Then lastly, we have the non-negativity constraints. That's W1, W2, in W1, comma W2, comma W3 greater than or equal to 0. That is actually those are the non-negativity constraints. Non-negativity constraints. Okay. All right. So that's the thing we have. So based on all that now, we have we also if you solve all this, right? If you solve all this using say any method, for instance, especially simplex method, because we have more than two variables. So let's talk about the solution in that situation. So solution, if you solve this normally, um, you get that optimal allocation, the optimal allocation of weights, the optimal allocation of weights is that W1 equals 0.6000, W2. So that's the proportion. So you should invest 60% in W1, 20%, that's 0.2000 in W2, and W3 is another 20%, 0.200 in W3. So in essence, it's like 60%. Okay, 60% in the first asset, 20% in the second asset, and this is 20% in the third asset. That's like just multiply each of them by 100. That's what that means. Now, that's the optimal solution. Normally, right, I should set up the whole system uh and start doing, and of course, this will definitely lead to Z. So Z is actually 0.1080. So it means that the total returns from all the investments, right? Okay, let me make that the same with this. So the Z, right? The objective function Z is now 0.1080. That means that the total return from all of my investment is 10.80%. So that's the optimal solution. If you set that up and you solve using simplex method, that is what you are going to get. So, but our focus here, that's just the problem statement so far. Now, uh, normally, right, if I have all the time, I should have done, set it up, and then I should have used simplex method to get all these results. But I'm giving this result up front because we have a bigger fish to fry, which is the sensitivity analysis, and that's exactly our focus. So let's go to the sensitivity analysis now. Sensitivity analysis. Okay. All right. Of course, we know the let imagine that we have the first the original problem, right? We know what that is, first of all, then we can appreciate the other situations. So I guess I want to lay it out one after the other for proper understanding. Okay. So first, one, we have the original problem. Original problem. Okay. The original problem was to maximize maximize Z equals 0.12 W1 plus 0.10 W2 plus 0.08 W3 subject to W1 plus W2 less than or equal to 0.8, W1 plus W3 less than or equal to another 0.8. Then, of course, you also have W1 plus W2 plus W3 equals 1. And of course, we have W1, W2, W3, all positive, all greater than or equal to 0. Okay? So that's the original problem, right? And for that, we got, again, we got W1 is 0.6, W2 is 0.2, W3 is 0.2 again, whereas Z is 0.10 8. We can just have it that way. So that's that. Now, can we check, can we check, um, so now we want to check how some changes affect each of these parts, right? So let's look at, for instance, mm, objective function coefficients. Yeah, I want to get them out one after the other for clear understanding. Okay. Mm, so we have the initial problem and the objective to that. Yeah. Okay. So now let's see. The first thing, like we said, right, is about the sensitivity analysis on objective function coefficients. Okay. So let's check that out first. Sensitivity analysis, sensitivity analysis on objective objective function coefficients. Okay. Now, can we look at a case? Let's look at case one where we have decrease. Case one, my one is looking strange. Uh, Let me just do it this way. Okay. Case one, let's check that. Let's check for, let's imagine we have decrease. We want to decrease coefficients, objective coefficients by 5%. Okay. All the objective coefficients want to decrease by 5%. So in that case, now it means we have a new Z prime. The original Z prime is 0.12, 0.10, 0.08. So if we decrease by 5%, it means that we are now going to have 95% of 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 the coefficients now. So you see 0.12, the original 0.12, we now multiply that by 0.95. So by multiplying by 0.95, you have automatically decreased it by 5%, right? So this is W1 plus the other one 0.10 times 0.95 W2 plus lastly 0.08 times 0.95 times W3. So now, I mean, by doing this, we have a new problem. We have, so you see Z prime is now 0.114 W1 plus 0.095 W2 plus 0.076 W3. So we have reduced all the coefficients. You know, the original coefficients were 0.12, 0.10, 0.08. So we have reduced them by 95%. So this is now the 95% value of each of the coefficients now. So it means we have our new problem now. So new problem. The problem is now new, and it is this. We now have to maximize. Now want to maximize Z prime. You know, I'm calling it Z prime because it's not the same thing again. So 0.114 W1 plus 0.095 W2 plus 0.076 W3 subject to subject to W1 plus W2 is less than or equal to 0.8. W1 plus W3 is less than or equal to 0.8. Then W1 plus W2 plus W3 is equal to 1. And of course, W1, W2, W3 is greater than or equal to 0. So you see, the coefficients now are what we are focused on. Look at that. Now, the interesting thing is, of course, is if you set it up again, do the simplex everything. So the solution here, I'll just write out the solution straight so that we don't keep. Of course, if you can check previous videos to see how to go about the simplex method. So here the solution now is still W1 equals 0.6, W2 W2 equals 0.2, and then W3 is still 0.2. But guess what? Our new objective function is now 0.1026. So you see, it was 0.108 before, but because the constraints have been reduced by 95%, the objective function is affected automatically. So you see here that this shows now, I mean, you have to set this up, use simplex method, and then you now end up getting 0.1026. So you can see that the objective function has reduced. So this shows a minor decrease. You know, the original Z we had before was 0.108. Now it's 0.1026. So this shows a minor decrease, a minor decrease in the maximum in the maximum Z, but but the optimal weights, but the optimal weights W1. So you can see W1, W2, W3 are still the same. W1, W2, W3 remain unchanged. Remain unchanged. So that is case one. Okay. That's case one when we focus on the coefficients. So let's talk about case two. I guess I want to change markers at this point. So let's talk about case two. Imagine case two where you increase objective coefficients, increase objective coefficients by 5%. So the changes can come in any way. So it's only that here we are increasing or decreasing by 5%. It doesn't have to be increased or decreased by 5%. You could just change those values arbitrarily or based on whatever you're doing. And you know, this is investment now. You are now saying, okay, if there are some other investment that have higher return values per unit, what will it amount to? But we are just using the case of increase in 5%. So you remember when we did decrease by 5%, right? So something was 100% before. So you now decrease it by 5%. That's why it led to 95%. So that's why we had to multiply each of the previous coefficient by 95%. But here we are increasing by 5%. So it means the 100% you had, you're adding 5% to it. So that means you're going to to get the new value, you're going to multiply by 105%, which is the same thing as 0.105, right? So our new, it means that our new Z prime prime is going to be something like 0.12 times 105%, that's 0.105 W1 plus 0.10 times 0.105 W2 plus 0.08 times 0.105 W3, so that the new Z prime prime is now 0.126 W1 plus 0.105 W2 plus 0.084 W3. That's what we have. So what's the new problem here? So the new problem in this case, we have changed the coefficients, and you don't have to change all the coefficients. You could change it in whatever form. You could just change one or two or all like we have changed here. So as far as one changes, it means the problem is redefined. So here now we have to maximize Z prime prime. Want to maximize Z prime prime equals 0.126 W1 plus 0.105 W2 plus 0.0084 W3. Now, subject to the same constraints, subject to W1 plus W2 less than or equal to 0.8, W1 plus W3 less than or equal to 0.8 again, and then W1 plus W2 plus W3 not exceeding 1, because of course you don't want to exceed 100%. Then W1, W2, W3 is all greater than or equal to 0. So that's the problem. That's a new problem now. But then we also have a new solution, and that is that. So the solution here, if you do the whole simplex thing, so you have W1 equals 0.6, W2 equals 0.2, W3 equals 0.2, but then Z prime prime is now 0.1134. So you see, 0.1134 is higher than what we got initially as optimal solution. So what that means is that though the the proportions have not changed, but the objective function has been affected. So you see that increase, the increase in Z is minor, okay? The increase in Z is minor, and the optimal solution the optimal solution remains the same. The optimal solution remains the same. That is the values of W1, W2, and W3 remain the same, indicating the robustness, indicating the robustness of the optimal widths, the robustness of the optimal widths against small changes, against small changes in objective coefficients. Of course, the objective coefficients here are like investment returns. That's more like investment returns. So decreasing the coefficient by 5% means reducing all the investment returns by 5%. And increasing by 5% means increasing all the investment returns per unit, rather, per unit, that is, by 5%. So what this is telling you is that if you increase the investment returns by 5% each, the optimal solution still remains the same. It still tells you that you should invest 60% in the first asset, 20% in the second asset, and 20% in the third asset. And then but then you now have um a slightly improved objective function, which is now 11.34% instead of the 10.8% you got initially. So don't forget, again, this can be also rendered in terms of percentage. So 11.34% is what you get here. And in the previous case, right, we ended up getting 10.26%, which was a reduction, uh, you know, a little bit of reduction from the 10.8% that you got in the optimal solution. Okay. So changing the coefficient, that is the investment returns, has a slight increase on the overall return, right? But I mean, it depending on the kind of the amount you're investing, right? The percent, 0.1% can mean a lot in an investment. That's really something to pay attention to. Okay, so that's one aspect. So we've considered the aspect of you know, talking about sensitivity analysis. Now we have talked about sensitivity analysis on objective function coefficients. Now, can we go to the constraint limits? Because we either talk about the objective function coefficients or constraint limits. So now let's talk about constraint limits. I guess I want to change this also to something else. Let me go purple in this case. So let's talk about sensitivity, sensitivity analysis on constraint limits, on constraint limits. That's the right hand side stuff. Okay. Now, can we consider case one? Let's look at case one in this case. Let's still focus on the 5% thing, increase or decrease, and see how it happens. So let's look at case one. For case one, a decrease the decrease constraint limits, decrease constraint limits by 5%. Okay. Decrease constraint limit by 5%. Of course, that's 100% minus 5%. That means you're going to have each of the constraint limits is now going to be 95%. So it's more like you're shrinking the feasible region. So what that simply means is this. You know, the original problem was that we have to always make reference to the original problem. So you have um so you have 0.8, 0.8. So you are shrinking those. Of course, you cannot shrink this one because that everything still has to add up to one. So you're only shrinking those 0.8 by 5%. Okay. So it means that now you're going to have the new problem. So that W1 plus W2 less than or equal to 0.8 now will now be, so you now have W1 plus 0 plus W2 is now 0.8 times 0.95. So, and that is 0.76. Same, W1 plus W3 less than 0.8 times 0.95. That is 0.76. So what's the new problem? I have the new problem to be what it was. So Z now is 0.12 W1. Okay, I mean let me make it formal, right? You want to maximize Z equals 0.12 W1 plus 0.10 W2 plus 0.08 W3, W3, okay, subject to W1 plus W2 is less than or equal to 0.76. You have literally shrunk the feasible region now. You know, yeah, the feasible region is shrinking. And then you also have W1 plus W3 is less than or equal to 0.76 because you have shrunk it by 5%. So 0.76 is 95% of 0.8. And of course, you know, this W1 plus W2 plus W3, W3 is one. There's nothing you can do about that. Everything has to add up to 100%. And then you have the inequality constraint W1, W2, W3, all greater than or equal to zero. Okay. Now, if you put this in under, if you take this through simplex, see the solution you get. The solution in this case would be W1 is now 0.2. So you see, you have shrunk the feasibility region. So W1 is 0.2, W2 is 0.24, and W3 is also 0.24, so that the new Z now, the new Z is now 0.1056. That means we're talking about, let me have this now. So we're talking about 10.56%. So you can see that the feasibility region has been shrunk. So in this case now, you are only going to make 10.56% on all your total portfolio instead of the 10.8% you had in the original case, in the original problem. Okay. So if the feasibility region is shrunk, this is bound to happen. All right. So that's case one, when you decrease constraint limit by 5%. What if we do case two, right? What if we do case two, where we increase we increase constraint limits by 5%. Okay. Increase constraint limit by 5%. Of course, just like I've been saying, that's like you had 100% before, so you're adding 5% to it. That's like 105%, which is the same thing as 0.105. When we shrunk it, it was 0.95 here. Okay. This is like same as 0.95. So here now, again, you have the same situation. You have your W1. Okay. You have W1 plus W2 less than or equal to 0.8. But now 0.8 times 0.105. And that would be 0.84. So you have the same thing, W1 plus W3 less than or equal to 0.8 times 0.105. That is 0.84. So what's the new problem now? So you have the problem has been reformulated because you have now by doing this now, 0.8, but 0.84 means you are expanding the feasibility region, okay? You're expanding the feasibility region, and that means that you now have a new problem, which is maximize Z equals 0.12 W1 plus 0.10 W2 plus 0.08 W3, subject to, say, W1 plus W2 is less than or equal to 0.84. It was 0.8 in the original problem. Now you have increased the feasibility region. W1 plus W3 is less than or equal to 0.84 again. And then you have W1 plus W2 plus W3 equals 1. And then W1, W2, W3 are all non-negative. And if you work this out, right, with this present situation, you'll see that so we can get the solution if you use if you set this up again and use simplex method. So I'm not worrying about that because I've already treated simplex method. I have like one or two examples thoroughly explained for simplex method, so you can just keep applying that. So here the solution would be say W1 equals 0.8 and W2 is 0.16, while W3 is also 0.16. For some fun, interesting reason, right? W2 and W3 always take the same proportion. Like you can see up here too, it's like the same proportion all the way. Okay. But so in this case, we have all these values that they are taking. So this is like 68%, 16%, 16%, all adding up to 100. But then what's the Z here? The Z is actually 0.1104. And like we know, that's 11.04%. So what all you have done here has increased the proportion for W1 has increased, whereas the one for W2 have actually reduced because it was 60, 20, 29, 68, 16, 16. So what this has done is that increasing, increasing, increasing the constraint limits, increasing the constraint limits allows allows a increasing the constraint limits allows a larger allows a larger allocation. So it's only allowing a larger allocation to to first asset, that's to W1, and then it's now raising it's not it's so that it's raising the maximum Z, you know. The original maximum Z was 10.8%. So By doing this now, it's raising the maximum Z, you know, from 10.8% to 11.04%. So in this case now, so increasing the the constraint limit is more or less like maybe you invested 80% of your funds in it before. Now you are now putting 84%. So it's more like you're increasing your investment in these things. That's basically the analogy that we get. Okay. So from that, right, we can actually have a we can have an overview, a summary of sensitivity analysis results. So let's do that as we bring this to a close, hopefully. Let me go purple now. Yeah, so let's talk about summary of sensitivity, sensitivity analysis results. So mind you, I didn't bother doing all the simplex method. Each time you perturb the solution, like maybe you change the constraint or you change the constraint limit or you change the objective coefficient, you have to go the whole simplex route again and see what the solution arrives about. I mean, I've provided all the solutions here just to see how those things have impact. So here, talking about objective talking about coefficient changes, objective coefficient changes, how does it affect anything, right? So we see that small changes of plus or minus 5%. So plus is increasing by 5%, minus is decreasing by 5% in the objective function, in the objective coefficient rather, in the objective coefficients do not alter, do not alter the, they don't really alter the optimal weights, do not alter the optimal weights W1, W2, and W3. Okay. Although they slightly impact the maximum objective function, although they slightly impact Z. So just like I said earlier, right? It doesn't have to be just plus or minus 5%. It could actually be okay, you're increasing the first return by 5%, the second by 2%, the third by 3%, whatever. So you can have a mix of all of these things. So whatever your specific situation is, just apply it. Maybe you are looking at the possibility of, say, the first asset per unit, 1 unit increases 5% in return, then the other one reduces 2% in return, and the third one increases 15% in return. You can have a whole mix of all of that. But the major thing is once you set up the new situation, you use simplex method to get a new solution, and then optimal solution, and then you compare it with the optimal solution of the original situation. Basically, that's what the whole idea of sensitivity analysis is. So let's talk about so we've talked about objective coefficient changes. How about constraint limit changes? Constraint limit changes. Constraint limit changes. So we see that adjusting the constraint limits, adjusting the constraint limits by plus or minus 5% so this automatically affects the optimal weights and objective. So they affect both the optimal weight and the objective function. Okay. Indicating that indicating that the solution is more sensitive The optimal solution of the original problem, right, sensitive, is more sensitive to constraint limits. It's more sensitive to constraint limits than objective coefficients. So if you really want to affect the system, you change the maybe your resource allocation, which is basically talking about investment, the how much you want to invest in a combination of the portfolio, basically. So with that, we come to the end of this video. If you have not subscribed so far, please be sure to do that right now because there's a lot to learn already and there's so much more coming your way. So don't forget to hit the notification bell also so you can always get alerted each time a new video is released. Then make sure to comment. Let me know if you need me to teach a topic or solve a problem. Then also like and share so that more people can have access to this great learning. Till I come your way again, keep optimizing. Don't forget, the next video is going to be a Python code to show all of these things I've demonstrated here, this original solution and all the perturbations, leading to sensitivity analysis. So watch out for that. See you then. Bye.